All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206, I want to say. All right, let's jump into it here. Okay. All right, and we are go. Okay, so this is what we did yesterday. Just going to do a quick recap just to get us on the same page. We also looked at another thing yesterday, which is called continuity, which is also kind of a fuzzy idea, but I wouldn't say it's as fuzzy as the idea of limits, but it's still kind of fuzzy, so I'll just quickly go over that. So last time I left you guys with some examples to try, which was based on some techniques I taught you about limits. Do I need to go over those? Maybe I should. Last time, we were talking about how to do limits, how to compute limits in general, like a short strategy to do them efficiently. Because on like a test, I'm going to ask you to do like a bunch of limits in one problem. It's going to be like, there's going to be one problem. It's going to be like A, B, C, D, maybe even E, and they're all going to be limits. And you're going to want to be able to do them very quickly. So you want to be able to do limits very efficiently. And so I gave you some general steps, a general approach to computing these limits. So the first thing is try to plug in the number. Now, the reason why that works was covered in yesterday's class. But if you can plug in the number and it works, chances are that's the answer. There's a little bit of times this can be wrong, such as like with a piecewise function, because remember, technically, it's not what the value of the function is that the limit cares about, it's what you're getting close to. But in a lot of the functions that we're looking at, you can literally just plug in the value and you'll get close to it just by definition of how it works, by continuity, which we spoke about afterwards. So chances are, if you plug in the number, it's going to work. This will work for all continuous functions, in fact. That's what's usually going on. Don't do this for if you have a piecewise function or it's just very complicated. And you might have division by zero or anything like that. But for simple things like this guy, you plug in the number and that will work because 3x minus 1, y equals 3x minus 1. It's a very smooth function, it's a straight line. Now, in the event that that doesn't work, right? That's the first thing you try. It's always the first thing you try or think about trying. The next thing is try to simplify so that you can plug in. So like if you have division by zero, try to see if you can get rid of it, see if you can rewrite stuff in a better way, a more efficient, a way where you can get to a point where you can plug stuff in. And sometimes that works, and that's great. That's awesome. Sometimes that doesn't work either. So step 3 would be, hey, maybe a special technique would work. Oh, this looks like something that a special technique might work on. So that was step 3. And in step 3, we had several special techniques. We had, and by the way, we're going to get some more. We had the limits of infinity of rational functions. If you have a ratio of polynomials, you can kind of figure out what's going on based on the powers in those polynomials. So if the highest power is on the bottom, it's going to go to 0. The highest power is on the top, it's going to go to plus or minus infinity. Just make sure you check the signs. If the highest power is the same on the top and bottom, it will go to the ratio of leading coefficients. So that was one special technique. Another special technique was squeeze theorem, which basically tells you if you can squeeze your limit between two things and those things go to the same number, it forces your limit to go to that number. It's usually very useful with trig functions. So if you have a limit with trig, squeeze theorem is one of the things you'll think about like first, right? When it comes to trig, you'll usually think squeeze theorem or the special trig limits, right? Which is, I think was the next one. Yeah, the special trig limits, right? These are just limits that you have them memorized and you can use them at any time. So that's another special technique. And yeah, so far we have 3 special techniques. We are going to see one more. We're going to see one more later on, but we have to talk about derivatives before we can see that. So yeah, so that was the next step in trying to find limits. Apply a special technique based on how it looks. So if you notice it's a limit at infinity of a rational function, there's a special technique for that. You can just use it. Another thing is to use your knowledge about how functions behave in relation to each other. So for example, if your x is going off to infinity, you know that any x increasing exponential will beat any increasing polynomial, right? So you can always know that that's going to be true, and you can use that to come to some conclusion. So it should be obvious, for example, that the limit as x approaches infinity of e to the x over this is going to be infinity, because e to the x is an increasing exponential. It's going to beat the polynomial to the 1000th power. It'll beat the polynomial to the millionth power. It doesn't matter what power the polynomial is to. E to the x will eventually get huge compared to this polynomial. So you can actually just know that, right? And you can call it just top heavy or something. Then you can also use the graphs, right? So you could do that, for example, with limit as x approaches 0 of 1 over x squared to get infinity, because you'll see that it shoots up on both sides. You can use that to figure out that the limit as x approaches 0 of 1 over x does not exist, because on one side it goes down and the other side it goes up. You can use a table of values, which is a valid approach, but it's usually not going to be very efficient. I mean, this is a very nice thing to plug in numbers into. You don't want to have to plug numbers into like something like this, right? Or something like this. Or something like that, right? Like if you're you're approaching 5, you do not want to be plugging in 4.999 into this thing, right? You just wouldn't do it. And of course, if it's infinity, what are you going to plug in? What is close to infinity, right? So table of values, it'll work in a lot of cases, in some cases, but it's just usually not efficient at all. That's like the last resort. And even then, I don't think it's going to work out most of the time. But yeah, it is something that in principle, you can understand what the limit is actually doing. It's inching closer. It's inching the input closer to some value, and you're looking at what the output is doing. So it was important for pedagogical reasons that I tell you about this, not necessarily because for practical reasons, like you're not going to use that. Okay, so right, we spoke about all that, and hopefully you took that to heart and practiced a lot of these limits. So I left these guys for you guys to try, and now we're up to yesterday's class. Okay, so here we realize that we can maneuver things to get those special trig limits involved. We understand that we need to remember other trig identities, like the double angle formula for sine. I expect you to remember that sine of 2x is 2 times sine x times cosine x. Expect you to remember that cosine of 2x is cosine squared x minus sine squared x, or 2 cosine squared minus 1, or 1 minus 2 sine squared. All that stuff I expect you to remember. I expect you to remember what is the sine of pi over 4, what is the sine of pi over 3, what is the sine of pi over 6, what is the sine of 5 pi over 6? What is the cosine of 7 pi over 3? Like all that stuff I expect you to remember. So yeah, they can show up at any time. And then we started a new topic, yay, continuity. It is easy to describe in words, especially if you're doing it hand wavy. It's not, it's not the hardest thing, actually. It's not the hardest thing in the world. But it is something that you have to get used to. Continuity, we defined a function to be continuous if it obeys this equation. So if a function at a point x equals a obeys this equation, we say that function is continuous at x equals a. Now, what that means is you're just able to draw through the point where x equals a without lifting your pencil off the page. There's no hole, there's no gap, there's no disruption. Everything is fine. Your graph is smooth. You're always there. You can get close to any point you want in that region. You don't have to jump over anything. And it turns out that this one equation captured that. we can call a function continuous in general, just continuous, not necessarily continuous at a point, if this equation holds for all points in the domain. And a function that's not continuous, we call it discontinuous. We call a function continuous everywhere if it's continuous on the entire real line. So that's just a phrase that you should know. And we also look at the steps that you would have to look at if you want to prove that something is continuous or check that something is continuous. You would tend to want to check three things. You want to know, is the function defined at the point? Does the limit exist at that point? And are these the same value? If any one of these three things break, it's not continuous. If all three hold, it is continuous at that point. And that's very important for you to understand that this is how you're going to check, because I'm going to ask you to do things like that. We also looked at the elementary continuous functions. These are functions that you can always assume are continuous on their domains. So from now on, hence and forevermore, at any point in time in class, you can tell me, oh, it's a polynomial, so it's continuous, and I'll believe you. Like I won't require justification for that statement or anything like that. You'll just know, you'll be able to say, oh, this rational function is continuous as long as x is not equal to -1, because that would mean the denominator 0. And I'm not going to ask you for any justification of that because it is an elementary continuous function. You can assume these functions are continuous on their domains. Polynomials, rational functions, radical functions, exponential functions, log functions, and trig functions. As long as you're in the domain of these functions, they will be continuous. And a lot of times when you're doing taking limits, you are plugging stuff into one of these kinds of functions, which is why the plug-in method works. It's not because taking a limit is the same as plugging in. It's definitely not. But it works because when you have a continuous function, the limit happens to be equal to plugging in the value, right? It's not that it's the same, they just happen to be the same in that one specific instance. Okay. So then we went and we looked at a bunch of examples. So we looked at the example, f of x equals x squared minus 1 over x minus 1. We said that, oh, if x is not equal to 1, we're fine. Why is that? Because it's a rational function, so we know it's fine if the denominator is not 0. So now we need to check where the denominator is 0, which is when x equals 1. And what we would notice is that the limit exists and its value was 2, but the function itself was undefined, and so that breaks the three steps that we have here. Right? Item 2 worked out, but item 1 didn't. Then we looked at this example, and I mentioned especially when you have piecewise functions, there's a certain way you want to read things. You want to look at the individual functions in each individual piece, see if they have any issues that you have to worry about, and then you look at the x values where your function is broken up about. These are all points where I don't know why I have an alarm set for now, but right. So for this guy, x equals 1 is the only problem point potentially. So you'll notice that if we're not at x equals 1, everything is fine because one function is x squared over x minus 1, and that is fine as long as x is not 1. And one function is 3, which is a polynomial, so that's fine everywhere. So there are no issues with the functions themselves. The only issue was with this guy, the fact that it's something different at 1 versus not at 1. So that's what we had to worry about. And yeah, so we did that. At 1, we checked the limit, we got 2. The function was defined, it was 3. These guys did not agree, therefore it's not continuous at that point. Therefore, it's only continuous away from that point. This one, a very similar function. We did the same thing. We noticed that if we're not at 1, everything is fine. If we are at 1, check the limit. The answer is 2. check the definition of the function. The answer is 2. Compare them. They're the same. It means you're continuous at 1, which means your function is continuous everywhere. Because I knew it was fine if I'm not at 1, and now I know it's fine if I am at 1. Similar thing here, did the same thing, played the same game. Hopefully this is jogging your memory a little bit. I'm not trying to reteach the same thing, but we go through this process a bunch of times. Then we spoke about removable and non-removable discontinuities. Pretty much if we can have a discontinuity where we can fix it by filling in some points, like we did, that's exactly what we did in this example up here. So this function was not continuous at x equals 1 because there was a hole. However, in this one, with the piecewise function, we defined the value of the function at that point to be 2. And essentially what that did was it filled in the hole, right? And so I removed the discontinuity. So it turns out that this function, x squared minus 1 over x minus 1, had a removable discontinuity. So we spoke about that. What else? Fun problems like this, you'll have to know how to do because I might ask them. So there are times when I give you a function and there are parts of that function that is unknown. So like there's like an a and a b here that you don't know what they are. And I'll ask you to find what a and b must be in order for the function to be continuous. And again, you go through the steps. You check the limit, you check the value of the function, you set them equal to each other, and then you can solve for a and b from doing that, right? Just knowing the definition of continuity will help you to solve those. We did 2 examples of that. Did another example here. I mostly just did this example to remind you of some trig and just get you used to seeing trig again. Spoke about one-sided continuity, that you can be continuous from the right or from the left. Sometimes that's important. For example, with the radical x, we know judging it by continuity on the left just isn't fair because it doesn't even exist over there. So it's not fair to call it discontinuous at 0 when it's like, really, you can't really be anything below 0 in the first place. It's just not fair. So we consider radical x to be continuous on its entire domain, including x equals 0, and we get that by one-sided continuity. We have properties of continuous functions. So if a function is continuous, any constant times that function is continuous. If you have 2 continuous functions, you can add or subtract them, and the result is a continuous function. If you have 2 continuous functions, you can multiply them, the result is a continuous function. If you divide them, the result is a continuous function, except if the denominator is 0. We had a nice theorem here, which I don't really expect you to remember that. What I do expect you to remember is what it gives us, that we can move limits inside and outside of continuous functions. So because sine of x is a continuous function, as you can see here, I can take the limit from outside to inside, right? I can like phase the limit through sine of x. Same thing for the exponential. If I have the limit outside, I can move it to inside the exponential. For the logarithm, if I have the limit outside, I can move the limit inside the logarithm, right? So continuous functions have that nice property, and that's what you need to remember from that theorem. That'll come in handy later on. Okay. With everything that we've said, we have a way of defining E. That's going to be important later. It's going to come up. It comes up often. It's going to come up in Calc 2 as well. So you should know those definitions for E. Calc 2 is where you're going to learn a new definition for E, which is this guy, but I'm not going to talk about it because it's above our pay grade. And that was yesterday's class. That took a long time. But we did a lot of heady stuff, so I thought it was good to just go over everything. Now we get to the new stuff that we want. We're still talking about continuity and some properties that we can get from it. So that's what we're going to deal with now. There's a very, very super important theorem. I'm definitely going to test on this theorem as well. will test you on this. And this would be like the typical problem I would test you on. Typical problem type. See, nothing on my sleeve. I'm telling you guys, hey, this is coming up. Okay, all right. So now let's talk about it, right? So there's a super important theorem called the intermediate value theorem. And it's important for a lot of reasons. Are we going to use it later? I think we are going to use it later. But it's an important theorem. And basically, it talks about a nice property that continuous functions have. So if you assume a function is continuous on some interval, right, and assume that there's a value between two y values of that function, right? So either f of a is less than or equal to some number which is less than or equal to f of b, or vice versa. F of b is less than or equal to some number less than or equal to f of a, right? Then it turns out there must exist a number in between a and b such that the output of the function will give you that number in between them. In other words, continuous functions will attain all intermediate y values. If I know two y values on the continuous function, then all y values in between will also be attained, all intermediate y values, right? So it's called the intermediate value theorem, right? So that's the theorem. Continuous functions will attain all intermediate y values. If you know there are two y values on this thing on the y-axis, it will hit every number in between them. So to illustrate, that's this function here. Here's a continuous function. There's no break, there's no gap, there's no hole. And here's a number that's in between f of b and f of a, right? It turns out that there will always be a number c that is in between a and b, such that when you plug that number into your function, the output will be whatever number is in between them. You will always be able to do this. If someone were to pick another number, oh, I want to get m. Well, there's going to be another c that I can pick whose output will be n. Oh, I want to get q. Well, there's going to be a c that I can pick whose output will give you q. You will always be able to do this. You will be able to attain any intermediate y value. So if you know any y value and there's a y value in between them, there will be an input that will give you that y value as an output, right? And that is important for all sorts of reasons. But okay. Take those off, right? So that's what that is saying, right? No matter what value you choose in between these y values, I can find an input that will give me that value as an output. And a way to say that in English is continuous functions will attain all intermediate y values. Give me two y values on the continuous function. This function will attain all y values in between them. It will attain all intermediate y values. Okay. So here's an example, and it also shows how you can actually use this theorem. So usually in this class, I'm pretty much going to ask you to use this theorem to solve an equation. Or not to solve an equation, more specifically, to show that an equation has a solution. So for example, here is the first example. And it's the only example because there's no real variety to this question. I'm going to ask you a question that looks pretty much like this. Show that this equation has at least one solution on this interval, right? So in other words, there is an x value that is in between -1 and 0 that will solve that equation. Now that equation is a cubic polynomial. This is x to the third power, right? Yeah, those are hard to solve in general. In pre-calc, you learned the rational roots theorem is one way to solve this, but it's not going to work here because you will check if x equals ±1 or ±3. You'll realize that neither of those give you 0, so you're kind of out of luck. Good luck factoring this. Can't really do it. So how do I know that I can solve this equation? Well, the thing is, you don't have to solve the equation. You just have to show that it has a solution. And here's how you would actually do that. What you will do is you would set a function to describe your equation. So usually you'd want to bring everything to one side and have it equal 0. Let me write it that way. Suppose I gave you that equation. Oh, should be an x value between -1 and 0 that makes x cubed plus 5x equals -3. So here's one thing you would do. Notice we have x cubed plus 5x plus 3 equals 0. What you're going to do is you're going to set up a function. Set f of x to be that side. So 1, bring everything to one side. 2, set f of x to be equal to the non-zero side. Non-zero in the sense that its expression isn't just strictly 0. Okay. Now, here's something you'll notice. That function, f, is actually a polynomial. So you can say since f of x is a polynomial, it is continuous on the entire real line. So definitely it's continuous on this interval, right? Yeah. In fact, f is continuous everywhere. Which, I mean, you don't have to write that, but I'm just reminding you. Polynomials are one of the elementary continuous functions. Right? So this is what I mean. This is an example of what I mean. You can say here, oh, f is a polynomial, therefore it's continuous on blah. And that is just a statement I will accept. You don't have to prove it's continuous. You don't have to go through those 3 steps that I mentioned and find, oh, let's take the limit and let's do this and let's check the output of the function. You don't have to do any of that. It's a polynomial. It's continuous everywhere. You can just say that. You can assume that. It's fine. So now, that's the first thing. Now, here's what you're going to do. You want to find 2 values in here that you can plug into your function so that you can bound the value around on this side, which in this case is going to be 0. So f is continuous on this, so I can therefore use the intermediate value theorem. This implies that applies. This is something I would expect to see if you're writing it out. And okay. So the intermediate value theorem applies. Now, the intermediate value theorem says that if I want to know that my function will output a certain number, specifically in this case, I want my function to output 0, which means n equals 0 in this case. So like there's a 0 in between these guys. All I have to do is show that my function is greater than 0 at some point and less than 0 at some point. And then that would mean that it has to attain 0 at some other point because of the intermediate value theorem. So that's what I'm going to do here. And the endpoints, they're included, so it might be nice to try them. So let's say note f of -1 equals, well, what does that equal? -1 cubed plus 5 times -1 plus 3 is -3. Notice that is less than 0. Also note, or plug in f of 0, that would be 0 cubed plus 5 times 0 plus 3. That is 3. That is positive. This means my f of -1, this means my f of 0 is less than 0, and my 0 is less than f of -1. This means there exists a C between -1 and 0. There's an intermediate input such that f of C would equal to that intermediate y value. This means that, of course, your C cubed plus 5 times C plus 3 equals 0. And this is the solution. We seek. This entire thing here would be the answer. There's some number in that interval such that the output would be 0, which is what we have in the function here. And so that is how you would work out that example. So that's what we have here, right? That's showing that a solution exists. So what's going on here is I have my function doing whatever. I don't even know what it looks like, right? This is your like f of x. And right, I'm on the interval -1 to 0. I found that my f of -1 was less than 0. Everybody's in the opposite order. Right, so this here is my f of -1. Then I found that my f of 0 is up here. Now, if the function is continuous, there are no breaks, no gaps, no jumps, no any of that. If I move from this point to that point, I have to cross the x-axis somewhere. Crossing the x-axis means you cross the line y equals 0. There must be a point in between -1 and 0 where the function crosses the x-axis. because there's no way to go from a negative number to a positive number in a continuous fashion without actually crossing the x-axis. We know it's because of the intermediate value theorem. So that's what happens. And this is what the C would be here. Now, notice that we never actually find the value of C. We don't care. You weren't asked to find the value of C. You just wanted to show that a solution exists. And that is super useful as well, because even though we don't know the answer, just knowing one is there actually gives us a lot of options. In a situation like this, numerical analysis would give us the options. We'll use some sort of algorithm to kind of zoom in on the answer. Like if I know it's in the window between -1 and 0, I can run some kind of algorithms like Newton-Raphson method, and then get a smaller window, get a smaller window, and get a smaller window. And I can get to the answer within any degree of accuracy I want. And of course, I wouldn't do that. A computer would do that. But the computer would check based on the intermediate value theorem that, oh, I expect the solution to be somewhere around here. Let's actually zoom in on it. So yeah, that's that. That's the intermediate value theorem. Continuous functions will attain all intermediate y values. And this is how you can use it to show that an equation must have at least one solution. This could have happened several times, but it will have at least one. And yeah. Any questions on this? Like I've been talking for a long time. Are we good? Are we? Okay. So we will wrap up our discussion of continuity right there. Now, some more things on limits. Nothing new to learn, really. Just have to state some things that we've kind of been using in the background, but I never actually explicitly stated them. So I have to be like responsible and actually state these things that we've actually been using. So it turns out that limits have very nice algebraic properties. And in me telling you the strategy on how to solve limits, how to compute limits, we were actually taking advantage of these strategies, these properties. So these are just things you should know about limits. Your limits, you can factor constants inside and outside of limits. So if you have the limit of a constant times a function, it's the same thing as the constant times the limit of that function. Right? So that is a property that limits have. Another thing you can know about limits is that if you can take the limit of a sum, it is the same as the sum of the limits. Limits will distribute across sums, which is nice. So the distributive law would work for limits. Remember, it doesn't work for logarithms. It doesn't work for sine or cosine. There are a bunch of functions that it doesn't work for. It happens to work for limits. Another thing is limits also distribute across products, which, I don't know, it's pretty crazy. There are not many things that distribute both across sums and products, right? Like, yeah, I don't think at this point in time you covered anything in mathematics unless you went ahead that would do both of these things. Like limits, yeah, limits are awesome. They're super nice in this way. You can distribute them across sums. You can distribute them across products. You can distribute them across divisions. Of course, that makes sense. If you can distribute it across multiplication, you should be able to distribute across division. Of course, the usual thing, make sure you're not dividing by 0. Limits can go inside and outside of powers, so that's nice. And that's kind of because a power function tends to be continuous. So you can slip the limit inside and out. But yeah, these are the properties of limits. You can move limits around in these ways, which is very nice. There are very few things that do all of these things. So Yeah, limits have some nice properties. So I just wanted to let you know that. We've actually been using this like the whole time, but we have to do that. We're going to talk about the precise definition of a limit now. So I left this one at the end. I wanted to have a very intuitive idea of what a limit is, know how to calculate one, so that now when we get to the theoretical stuff, it's going to not be so bad. So in one sense, this is the only time in this class where I'm really going to ask you to like prove anything, but at the same time, it's going to be straightforward in the sense that I'm going to give you like a template in which to do it. So you don't have to like know about proving stuff in general. I'm going to tell you how to do it. But yeah, we're going to talk about the precise definition of a limit. We want to know what a limit is exactly, not just this fuzzy notion of, oh, if x gets close to this, the y gets close to that. From a mathematical perspective, that's very vague, because what do you mean by close? Close to one person is not necessarily close to the other person, right? Which we mentioned before. So now we want to make that precise. So here is the definition. We say the limit as x approaches a of f of x is L, and we write this symbol, same one we've always been writing, if the following happens. This is read for all. If for all epsilon greater than 0, that's epsilon, it's a Greek letter. There exists, this backwards E is there exists. A delta greater than 0, so this is lowercase delta, another Greek symbol, such that if the difference between your x and your a is less than delta, then the difference between your output and your L will be epsilon. In other words, this is saying that if the x values get close, right? So before, the x value getting close to a was a very vague idea. But here we're making it precise. What do you mean by close? I mean specifically within delta distance. It's within delta units of a. So that's what I mean specifically by close in this case. If the x gets close to a, the y values, which is the outputs, the f of x's, will get close to L. So that's what this is saying right here. So this is pretty much saying is that the y values get close to L. But here, again, close isn't some vague term. It is defined by this number epsilon, right? So there's a particular number that we have in mind. And the nice thing about this definition is it leaves that number up to the interpretation of the user. So every person can pick their own epsilon, right? So that's why it says for all epsilon. One person can decide that this is close enough. Another person can say, no, that's not close enough. I want this close. And it doesn't matter. They can both choose their tolerance and it'll be fine. It'll still work out. That's what it means for a limit to exist. You can get as close as you want. and you can measure how close you're getting with epsilons and deltas. So basically, we say this is true. The limit as x approaches a of f of x is L if, when the x's get close to a within delta units, the y values will get close to L within epsilon units. So just kind of illustrate what that means. So there is going to be a tolerance that they have for the how close you want the y values to get. So let's say there's an interval over here where it's epsilon units. So I want to get close to L within this window, right? And so that creates a window over here. So now, as a result of that choice, someone else has to pick another window, right? So they have to pick, say, a window on this side where it's delta units in either direction, such that that window is projected. Notice that this creates like a box. And you'll notice that within that box, all the y value outputs will be within epsilon units of the L. Right? So within that box, if your x values are so close that they're within that box, then your y values will be so close that they're within that other box. That's basically what it is, right? So how we want to think about this is that given a tolerance epsilon for the y values, someone will say, I want my y values to be this close, right? That's going to be, you have no control over that. Someone's going to say, this is what close means to me. If you get the x values close to A, I want the y values to be this close to L to convince me that the limit exists. And a random person can give you whatever random epsilon they want, right? So you're given the tolerance, like you have no control over this. You do not control this. Right? So epsilon is something you're given, you have no control over. However, what you control is the delta, right? So given someone's telling you, oh, I want my y values to be this close, you are going to respond with, okay, here, I will tell you what delta you need, right? So you need to find delta. To make that happen. So someone will say, I want to convince me that the limit will exist, the y values have to get this close to L. And then you would respond to that person, okay, I can do that. Just make sure that the x values are this close to A and you will have what you want. And then someone else can come, oh, I have a different epsilon. I want, so someone else can come in and be like, all right, my epsilon is this. I want a smaller window. I want to get even closer, right? So that's the new epsilon distance. So that goes here. And then what you can respond with is, well, just make sure your x's are that close, and then you'll have everything in that box that you want, right? That's the idea. Like once someone chooses the epsilon window, you'll be able to choose the delta window so that all y values are within their tolerance. So that's the idea. you can make the x values get close to A, and then the y values will get close to L. How close to A? Within delta units. How close will they get to L? Within epsilon units. That makes close specific. All right, so that's the definition. If I ask you about this, I might give you points for the definition, maybe like 1 point or something. So if you can memorize the definition, it would be cool. So now, the thing is your delta may depend on epsilon. So I'm going to show you an example of what this would actually look like, of you going through a process and showing and proving a limit exists. Then I'm going to give you like the template, and then we're going to do it again, but over and over following the template. And I'll show you a little hiccup that can happen, and we'll deal with that. So we have 3 examples here. So here, I want you to notice that you're given the answer, right? So notice answers are given, right? So I know that the answer is 5. I know that the answer is 6. I know that the answer is 4. Or let's just say I'm proposing that the answer is 5. I'm proposing that the answer is 6. I'm proposing that the answer is 4. And I have to convince someone else. So whenever you see proof or prove that the limit exists, not compute the limit, not evaluate the limit. So note, it says prove, not compute or evaluate. And the idea is to prove a limit is a certain value. You would use the epsilon delta definition. Right, so that's what this guy's called. It's called the epsilon delta definition. Okay. Now, I know it's confusing, but I'm going to show you how to use this definition, right? So remember, epsilon is the tolerance you're given for the y values. You have no control over it. Your job is to find the tolerance for the x values that makes the tolerance for the y values work out, right? You want to show that if someone tells you epsilon, I want my y values to be epsilon close to L, you will simply say, oh, choose this delta. And if you can get the x values to be within that distance of A, you will have all your y values to be within epsilon units of L, right? So that's what you have to respond with. So if I want you to do this, I might state this something like use the epsilon delta definition to prove that the limit as x approaches 4 of 3x minus 7 is 5, which, I mean, you could just plug in 4 here, right, and compute 5. But that's not what we're doing. We want to prove that this is the answer. We want to show that if x gets close to 4, your y values will get close to 5. So here's how it's going to look. So you would say, let epsilon greater than 0 be given, right? You have no control over it. Someone gives that to you. this is the epsilon I want. Okay, now you're going to choose delta equals blank. Now we will fill this in later. Okay. Then if x minus 4, because that's your A, is less than delta units apart, right, in absolute values. Absolute values measures the distance between x and 4. So if your x is that close to 4, then you pretty much want to say your f of x, your y value, minus L, which in this case is 5. Maybe I should color code this. So you're going to plug in the 4 there. You're going to plug in the 5 there. So ultimately, what you want to show is that this guy, blank, is going to ultimately be less than epsilon, right? That's basically what you want to say. If you pick this delta, then this expression is going to be less than epsilon. And that is going to be the proof. Now, the thing is, what do you fill these in with, right? So, okay, and that will end the proof. You won't have to do this, but customarily end the proof by doing a little box here. So here's what you're going to do, which you're ultimately going to come back and put in this position. So this now here is like your scratch work. So what you're really going to do is you're going to go to the side, you're going to figure out what the answer is, and then you're going to come back and pretend that you knew what the answer was all along. Oh, just choose this. And they're like, really? And they're going to work it out and like, oh, it's less than epsilon. Wow, how did you know I had to pick that? But really you calculated it, right? So here is where you're going to do it. So I'm going to show you how to get the green calculations, what you're going to put in here. Notice that we want f of x minus 5 to be less than epsilon. But what is that? Well, f of x is 3x minus 7. I'm going to come over here and plug it in. We want that. Now, if I do that, what I really have here now is 3x minus 12. Okay. Now, what I can do is I can factor out a 3 out of these absolute values. Okay. Now, this is the point. This is very important. It's what you want to get. Notice here the x minus 4. That is like the x minus a, right, from up here. You want to get that. right? Because that's going to tell you how to choose your delta. So what you're going to realize here is that your x minus 4 in absolute value is going to be less than, well, you divide both sides by 3, right? So you would get epsilon divided by 3, epsilon over 3. That guy is your delta. And that's what you're going to fill in. So you're going to come up here and you're going to be like, oh, choose delta equals epsilon over 3, right? So if someone comes and tells you, oh, I want to be within 3 units of the y value, then you would say, oh, just make sure your x values are within 1 unit close. Oh, I want to be within 1/3 of a unit of the y value. Oh, just make sure that your x value gets within 1/9 of a unit close, right? Whatever they tell you, you can respond to them immediately. Oh, this is the tolerance you need, right? Whatever tolerance you want with the y values, just make your x values 1/3 tighter and you will get the result that you want. How do you know I will get the result that you want? Well, try it. If you go here and you start plugging that in, well, this is going to be equal to 3x minus 7 minus 5. This is 3x minus 12, which is 3 times x minus 4. But I know that that is less than 3 times delta, right? Because that is less than delta. But what is delta? I just told you delta was epsilon over 3. And so this is equal to 3 times epsilon over 3. 3's cancel. And you got epsilon. Wow, that was exactly the right number. How did you know? Well, you did it down here, right? So that's kind of the idea. So a fully worked out answer to a problem like this is exactly this, actually, right? You're going to literally write this down and you're going to fill in the spaces based on the calculations you do on the side, right? So technically you're proving something, but it's paint by numbers. I'm telling you exactly what to write down to prove it. Like the only thing that you have to do is like these calculations here, trying to get the x minus a out of this f of x minus L, which there's a situation in which it can be tricky, but I'm going to tell you about that situation. I'm not sure I'm going to test you on the situation. Should I even tell you? I don't know. I don't know. Maybe I'll put it as a bonus problem. So we can use this template to answer problems like this. Now, when you become a math major, if you become a math major, I don't know if anyone's going to be a math major, you'll learn about how to prove things in general, and this proof is going to make way more sense to you because you'll have a lot of background behind it. But for some reason, it's in the Calc 1 curriculum, and it's kind of hard to teach you how to prove stuff in general on the spot. So I'm pretty much going to give you the template of how to prove it. And hopefully me explaining it in words kind of fills in the gaps. But here's the template. You are going to write, let epsilon greater than 0 be given. Then you're going to write choose delta equals blank. And here you must find the delta that works. May be a function of epsilon, right? So in this case, your delta was epsilon over 3. That's like some function of epsilon, right? So you're going to fill in that value, but otherwise you're writing down what you see right here in white. Then if x minus A is less than delta. So again, here you need to fill in then we have absolute value. What did I put L in? Blue. So maybe I'll put this in green. F of x minus L, we're going to fill in, equals to f of x, fill in, minus L, equals blank. It must end with less than epsilon. Put a little box right here and shade it. And what you're going to do here is you're going to fill in the calculations to show that your f of x minus L is actually less than epsilon. And how you fill in those calculations is that you force it to happen. So you go to the side and solve for exactly what you want, f of x minus L less than epsilon. You must get your x minus a from here to replace with delta. Yeah, and that's pretty much it. That's how you would do this problem. Let me show you another example. This one. Here, prove that this limit equals 6. So how are we going to do it? Well, same way we always do it. Same thing we do every night, Pinky. Let epsilon greater than 0 be given. Choose delta equals blank. Then if x minus a, which is 3 over 2 in this case, is less than delta, we have that f of x minus L, which is 4x squared minus 9 over 2x minus 3, minus 6, blank. I want to end with a less than epsilon. How do I figure out what these blanks should be? Well, I go to the side. So I want this thing. I want 4x squared minus 9 over 2x minus 3 minus 6 to be less than epsilon. Well, what does that mean, Basil? Okay, so I would actually just what can I do here? Combine these. 6 times that, that's 12x minus 18. So that would be 4x squared minus 12x plus 9 over 2x minus 3. Would that actually factor? 2x minus 3, x plus x minus 3. Yeah, it was even nicer. You didn't have to do all that. 4x squared minus 9, difference of squares. This is actually 2x minus 3 times 2x plus 3. That's nice. So this cancels that. Let's see if we can get that delta anywhere. So this is 2x plus 3 minus 6. It's 2x minus 3. If I factor out a 2, I get x minus 3 over 2. And that is the guy we wanted because that's right here, x minus 3 over 2. So that's my delta. So here this would mean that delta is less than epsilon over 2. So I would choose that to be my delta. So I'm going to go up here. I'm going to put epsilon over 2. Now you're going to go back here and you're going to show that that is actually going to work out. I don't know how this is going to go in here. Okay, so you're going to have this, and then you're going to just kind of regurgitate these calculations, but you know the delta ahead of time. Difference of squares. This is equal to 2x plus 3 minus 6. This is equal to 2x minus 3. Equals to 2 times x minus 3 over 2. That's delta. That's 2 delta. But delta is equal to epsilon over 2. And that is epsilon. Okay, so ultimately we showed that f of x minus L is less than epsilon once our x value is within this many units close. So that's that. I mean, this example is going to be a little bit complicated. You have to do difference of squares. You have to choose to make up a delta and choose minimums. That's the summer. I think I'll forget about this. Should leave it there though. Because I have done this example before. If you're interested, I can show you where the solution is, but I will mention. I mean, it looks very simple, but it's actually not, right? This guy kind of looks like it would be easier than that guy, but it's actually not. It's actually significantly more complicated. I don't have to worry about. Okay, let's see. What else do I have to tell you here? Well, I'll just mention these things and then we'll take a break. Because based on this new definition of what a limit is, it turns out we can redefine some of the other definitions that we had. So continuity, the definition for continuity can be restated in this way if you wanted to prove continuity in general. So remember, continuity says that the limit equals f of a, the value of the function. And basically, you go to the limit definition, and instead of L, you put f of a, right? That's the continuity. So if this is true, so if this is true, it shows that f of x is continuous at a. You can also talk about other kinds of definitions in this case, like what does it mean for a limit to go off to infinity? Basically, it means that you can pick any number you want, and there's a delta such that if your x gets close to that, you'll be bigger than that number, no matter how big the number was that you picked. Negative infinity means something similar. You can pick any negative number you want. There will be a delta so that if your x gets that close, it will be less than that number. You can get less than any negative number anyone chooses. You can get bigger than any positive number anyone chooses here. I don't think I'll ask you about this, but it's kind of something that I'm supposed to tell you about. So just to kind of illustrate what I mean here. Again, so you have a function doing this, a function doing that. And someone comes and say, oh, I'm going to pick a number m, right? The idea is you should be able to get close enough to your a within delta units so that every y value is larger than m. And you'll always be able to do this. If someone were to pick an m up here, I can still get closer to a so that the y value is bigger, right? You'll always be able to get close enough to a to get bigger than any number they come up with. So that's what this definition means. But yeah. What we'll do now is we'll take a break. And after that, we will talk about, I think, something fun. It's going to start with average rate of change. It's going to be very different from what we've been talking about, continuity and limits and all that stuff. But it's going to be a nice change. It's going to be, I think it's going to be fun. We're going to finally work on solving the rate problem. It turns out we've built up enough machinery to do that. So I will say 10 minutes, maybe 12. We can come back at 7:40. Give you guys a break. We've been talking about very heady stuff. But I mentioned to you what I would be testing you on, stuff that you wouldn't have to worry about. So just pay attention to the notes and pay attention to what I'm saying. You should be fine. It's the summer. It's very tight. So I don't want to make anything harder than it has to be. You don't have much time to study anyway. So pretty much worry about what I tell you to worry about. I pretty much point out what types of questions I would ask you. So make sure you know those. Yeah, that's it for now. We are going to pause here.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Okay, and we're back. All right, so let's get rid of all that stuff. Let's talk about something nice. I want us to actually talk about the rate problem. So throwback way last week. By the way, again, I posted the link to the notes in the chat. Throwback to way last week, first class, I spoke about what calculus was about. I told you it's about two main things. Those are the two biggest things that calculus was invented to solve. There was a theorem that told us, oh, these two things are really kind of two sides of the same coin. There's fundamental theorem of calculus. And by trying to solve these problems, we get a lot of side benefits out of it. So now we're going to talk about one of these problems, and that is the rate problem. So vaguely stated, it's like, can you think of like a mathematically sophisticated and relatively comprehensive way to talk about how fast things change? What is the rate of change of something? And we want to do so in more of an instantaneous sense. We can measure how fast something would change pretty well on average, you know. So I can, for example, I think an example I gave was like tides coming in and out. Like I can start my clock at some point in the day, mark where the tide is, and then come back an hour from now and mark where it is, or 5 minutes from an hour, or whatever. And I'll be able to say, oh, on average, you know, every 5 minutes, it rises by this much. You'll be able to say that. But if someone were to say in an instant, like I want to know like the current moment, how fast is it moving at this current moment? That was a lot more difficult. That was essentially what the rate problem is. We're trying to figure out how fast things change, how fast things move. But before we can get to that, we need to talk about something else that's pretty important: average rate of change. And that is this. So the average rate of change is kind of like the thing I just mentioned, how you can measure it over some large time interval. Could be a small time interval, but the idea is it's not an instant. And you can measure how something changes on average over some interval. So if f of x is a function defined on AB, as we're seeing here, the average rate of change of f of x on AB is defined to be this equation: f of b minus f of a over b minus a, right? One thing I want you to appreciate is it's actually the slope of what's called a secant line. So you just need to know that it's called a secant line. You don't need to know why it's called a secant line or anything like that. But it's called a secant line. So a secant line is a line that connects the two different points on the function. So here's my pretend function f of x. Oh boy, am I going to be able to draw a straight line here? Okay, it's not so bad. Okay, that could have been much worse. All right, so this green line here is called the secant line, right? It's a line that cuts through a function, 2 points. So what do you notice you can do now is you can actually measure the slope of this line. So we know how to measure slope usually. We have something like call this x1, call this x2, call this y, that would be y2, call this y1, right? So you have x1, y1, that's this coordinate here. And then you have x2, y2, that's this coordinate here. And you can actually measure the slope of this line. So if you know the two coordinates, you can actually measure the slope. So that's what we're going to do here, called the slope of the secant line. It's m secant. Some room, man. Okay, so what we would do is, of course, well, that's y2 minus y1 over x2 minus x1. And your y2 was f of b, your y1 is f of a. Your x2 is b, your x1 is a. Not much to go about there. But yeah, that's the slope of the secant line. Right? It turns out it can be interpreted as the average rate of change. In other words, how does the output of our function change on average per unit change in the input, right? So here's an example to illustrate this. And again, full disclosure, I'm going to ask you a question like this. It's another one of those questions where it's not difficult, just know that it's coming up and know how to do it. So I don't know if I should put that in green or red. Okay, and it's pretty much going to be stated exactly like this. I'm going to give you a function f of x, and I'm going to tell you, find the average rate of change of this function on this interval. And it's just a matter of you knowing this definition and computing it, right? And of course, the interpretation behind this is that it's giving us the average rate of change of the output in relation to the input, right? So here, you'll notice that the interval given is -1 to 3. That's like your A and your B, right? So A in this picture is the left endpoint of your interval, the left x value, B is the right. And that is your f of x. So if I wanted to compute the average rate of change, this is going to be f of b minus f of a over b minus a. Right? So that's actually f of 3 minus f of -1 over 3 minus a -1. So what is f of 3? Well, this is our f here. So I'm going to plug in 3 into that. So this is 4 minus 9. Well, it is 9, but let me write this as 3 squared. Then I'm going to plug in -1 into that. This is going to be 4 minus 1 squared all over, well, that's just going to be 4. 4 minus 9 is -5. 4 minus 1 is 3. So this is going to be -2. So this is the average rate of change of f of x on -1, 3. And that's it. That's there. It's not any more complicated than that. But it's going to be a very important stepping stone to what we're going to be doing, right? So this is how you can find how something changes on average. Pretty much you measure the y value at one point, go over somewhere else, measure it again. The two inputs you can think of as a time interval. I measure it now, I measure it later. and I know what the outputs are, I can tell you how much it's changing on average, right? So that gives you the average rate of change. Now, the interpretation of this number, as I mentioned, it's the average rate of change. It tells you how the function will change. So if here I look at my f of x equals, I think it was 4 minus x squared. Okay, so let's say I had this picture here. And 4 minus x squared. Suppose that is 4 minus x squared. I am on the interval -1 to 3, I think. So I know, well, we would know that this here is at 2, this here is at -2. So I am at -1 to 3. Just make it that. And so I'm moving from this point to not drawn to scale, obviously, to this point here, right? And essentially, oh, that looks really bad. Realign. Okay, so that's our guy, Mr. Secant Line. We know that this goes through at -2 and 2. Okay, so at -1, this was at level 3. And at 3, this was at level, what was it, -5? I think it was -5. Okay, so now here is what we want to measure. So let's look at how much the y value changed. Let me use pink. So here, 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 this is the change in y value. Of course, the change in y value is going to, it went from a level 3 to a level -5. So that's going to be 3 minus a -5. That is 8 units. Or let me do final minus initial. It actually fell, right? It started at 3 and ended at -5. So it's -5 minus a -3, it's -8 units. Where the -8 units, the minus means a decrease. So the y value decreased, right? How much did it decrease? By 8 units. Okay, so now if we look at the corresponding x values, so it went from here. So now if we look at the change in x values, that would be, the x value was from 3 to -1, 3 minus -1. So this is 4, right? So notice that in the span of time, the y value decreased by 8 in the time that it took the x values to increase by 4. So if you do these guys together, so someone can ask, how has y changed on average per unit x? And the answer would be, well, the y decreased by 8 over 4 units, so here it's -2. And what that means is it's -2 units decrease per unit x increase. Okay, so what you'll notice is that on average, this thing is falling like 2 units every 1 unit increase in x. So by the time x hits 0, on average, it's going to fall by 2. Now, notice that the on average is very important because it didn't actually do that. Notice that between -1 and 0, you actually had an increase in the y value, right? So notice y increased here. So it's not like it's always decreasing. It's just decreasing on average. It was decreasing for much longer than it was increasing, right? So here, y increased, but y is decreasing on average. Right? And what is a measure of how much it's decreasing on average? Well, -2. It falls by 2 units. So it was at, what was it, 3? On average, at x is -1, if I move to 0, it's going to drop to 1. Then I move over, it's going to drop to -1. Then I move over, it's going to drop to -2. You'll realize that every time I move over 1 unit, it drops by 2 units. Where would you expect it to be after I move over 4 times? You'd expect it to be at -5, right? If you take 3 minus 2 4 times, you would get to -5. So that's kind of how the y value is changing on average. It was decreasing on average by 2 units for every 1 unit x. So that tells you how the y value is changing on average. So that is what this is about, the average rate of change. You can actually measure how the y value is changing on average with respect to x. So the average rate of change of f of x on AB is how much y equals f of x changes on average with respect to x, where a negative Average rate of change indicates y decreased. Okay, cool. So that's average rate of change. Yeah, that's it. Now that's going to be important for us later, but it is something that we need to know how to calculate. And it's pretty much just calculating that. Now, here's something interesting. Why don't we change the notation a bit? And I'm going to do this because I want to do something else later. And I want the formula to look like it looks in like the textbook and the form that I want you to write it in. So I'm going to change the notation a bit here. Okay. So what I'm going to do is I'm going to relabel A and B. And I'm going to rewrite them in terms of the distance B is from A. Okay, so what I'm going to do is I'm going to set A equals X, it's some X value, and assume B is H units from X. So here, this is going to be X. Over here, then this is going to be X plus H. So the distance between these here is H. Now, if that is X, this would be, this is X, the corresponding Y value would be f of X. And if this is X plus H, the corresponding Y value would be f of X plus H. So now that would be your X1, your X2, your Y1 and your Y2. So now if you measure the slope of the secant by this formula, well, you get Y2 minus Y1 over X2 minus X1. Now if I plug that in, Y2 was f of X plus H. Y1 is f of X over X2 is X plus H. X1 is just X. So the X's cancel, get X minus X. And simplifying here, you get f of X plus H minus f of X all over H. Look at that, gasp, it's the difference quotient. Who saw that coming? I'm sure you all saw it coming. Gasp. It's the difference quotient. Let's all pretend like we're surprised, you know, like surprised. It's the difference quotient. Like once you saw me write the f of X plus H, you knew it was coming. Come on, that was a total giveaway. It's the difference quotient. Right? So it turns out the difference quotient is also measuring an average rate of change. That's why it's important. That's actually why in pre-calculus and all that, they randomly ask you to compute this thing, and you're like, why? Why do I need to do this? Well, it's because it's meaningful in the sense of finding average rate of change. And as we're going to see, it's meaningful in other ways as well. So with that, now that we understand average rate of change, what it's meant to calculate, how to calculate it, and we realized that the difference quotient can be repurposed to measure average rate of change. In fact, that's what it was created to measure. Let's actually attack the rate problem. So attack on rate problem. All right, so what we're going to do now is we're going to figure out how to solve the rate problem. Which is like a very vague problem. Like, how are you going to figure out how fast any random thing is moving? That doesn't even make sense. That's not even a problem statement. So here's how we're going to do it. The way math people always do everything. They figure out how to solve a simpler case, and then they extrapolate it to the more difficult cases, right? So I mean, you saw in high school geometry how you figured out the area of a circle. You first figure out the area of a rectangle, then the area of a triangle. Then you realize that a circle, you can look at it as like a bunch of pizza slices where they're all just mini triangles. When you turn out the triangles and you rearrange them, you can rearrange them into a parallelogram. And then by finding the area of that parallelogram, you get that pi r squared, right? So by us knowing how to find the area of a rectangle, we can figure out how to find the area of some weird shape like a circle, right? And that's the same idea we're going to use here. We're going to figure out how to solve the rate problem in a very simple case, right? Nothing crazy going on. Everything is just smooth. And then we're going to try to figure out, well, how would we do this in general now? So here is the problem. It's like the motivating example to why we would even have this idea. So suppose you're tracking an object, right? It's moving at constant speed. You probably don't know what the speed is. So you start taking some measurements. So you start timing it with a stopwatch, and you notice that, okay, I've been watching this object for a while. It's been 3 hours, and I noticed that it's really zipping. It's traveled 150 miles in 3 hours, right? So now I'm going to lead the witness suggestively into what we can actually gain from that information. So let's first like graph it. Graph the distance traveled over time in the correct color. So here, notice that we'll have this. Boom. Let me put that distance in miles. And we have time in hours, right? Because they gave us hours and miles up here. And we're told that we pretend that the distance from where we are right now is distance 0. It starts at distance 0. So this is where it begins. Okay. And then we know eventually, after 3 hours, the distance is 150 miles. So that's the coordinate at 3 hours. So here is the 150. Okay. Now, we're told that it's moving at constant speed, right? Which means it's not speeding up, it's not slowing down. So we're not expecting it to cover more distance at some times and less distance at other times. So it has to travel in a straight line, right? If we're measuring distance, like every time the clock moves a second, it's the same amount of distance it's traveling. It's not speeding up or slowing down. So the graph of this would have to be a straight line. So that is the graph of distance versus time. So if I were to ask, well, how far is it after 1 hour, right? I can use this line to figure out how far it would have traveled. And how far has it traveled after 2 hours? I can use this line to figure out how far it would have traveled. And you can figure out here that, well, it's kind of evenly divided. So this should be like a 50, this should be like 100 or whatever. But the two important points I would say is the ones that we know for sure. There's a 0, 0 in the very beginning, and there's a 3, 150. So that's what the graph would look like, right? Straight line, nothing crazy, nothing out of the ordinary, nothing fancy. Just it's moving at constant speed. So it's not like a haphazard graph. It's just like straight shot. All right, cool. Now B, the question is, what is the slope of the graph? So obviously the graph is a straight line. I know how to measure the slope of a straight line. We all know since algebra class. So the slope is going to be, well, y2 minus y1 over x2 minus x1, which is 150 minus 0 over 3 minus 0. So this is using x1, y1 equals the origin, and x2, y2 equals 3, 150. So that actually becomes 50, 150 over 3. Right, so that's the slope of this this graph here. Part C, interpret your answer to part B. Okay, so if you had to interpret this number, haven't had to ask a question in a while, need to make sure that you guys are alive. How would you interpret that number, that 50? What does it mean? Like if within this context, right? Like someone told you, okay, that this, you do this, you get 50. Like 50 what? Like what is that 50?
Is it 50 miles per hour?
It's 50 miles per hour, right? How do I know? I can, because the 150, the y values are measuring miles, right? That's what the axis is labeled as. So this is not just 150 minus 0, it's 150. It's 150 miles minus 0 miles. So that's the units of the top. And the bottom, it's 3 hours minus 0 hours. So this just becomes 50 miles divided by hour. And so this is what we know as miles per hour, right? 50 miles per hour. Turns out that's this is the speed of the object. I do want you to appreciate that what we've actually done is very similar to finding an average rate of change. I just found the slope of a straight line that passes through 2 points on some function. I can think of this as finding the average rate of change. What it would mean is if you have an object traveling and in 3 hours it traveled 150 miles, then on average it must have traveled 50 miles every hour. So after the first hour, it's at 50 miles out. Second hour, it's 100 miles out. Third hour, it'll be 150 miles out. Every hour, it'll be covering 50 miles. This is known as speed, right? Speed is the rate of change of distance over time, right? How much distance are you covering over time, right? So speed, this is the distance over time. Right? So that's actually speed. I mean, it's technically we're measuring velocity. Speed is actually the magnitude of velocity. So yeah. Or the uninitiated would call it speed. That's how fast the object is moving, 50 miles per hour. So I want you to notice that, it's interesting that the slope was equivalent to speed here, right? But that actually gives the mathematician a great idea. In this very simple case, I could think of slope as measuring the speed of something. How fast is it changing? If someone were to ask me, how fast is your distance changing in relation to time? The answer would be 50, which means that's the speed. I can use the slope to measure the speed, which is like the average rate of change. So there's this idea here about that slope can somehow be equated to speed, right? And that's that gives us enough to kind of chew on. So now the idea is, can we generalize this? And so now we deal with the harder problem. What if the object was not moving at constant speed, right? Like it's not a straight line, it's a curve. It starts out very slow traveling and then it speeds up, right? So that would get a graph that looks like this. In fact, this one was going a little bit faster, then slowed down, then started speeding up. This guy actually came back a little bit. He reversed a little bit and then went back. So this object is doing all sorts of crazy things, right? So the distance from the start, it actually got closer to start. It actually started reversing and then started speeding up the other way. So this is actually a very complicated moving object. It's actually an object that's moving back and forth is what this would look like. Moves back a little and then shoots forward and starts speeding up as it's shooting forward. So that's the question, like, what if it wasn't moving at constant speed? Well, we can't really measure speed now in an instantaneous sense. Moreover, notice that average speed is not actual instantaneous speed anymore. How do we know? We're faster. The object is moving faster in this region than in this region, just for example, right? Here, as my x moves a little bit, it covers like this level of distance, whereas here, as my x moves there, it covers a larger distance, which means it's moving faster. So this average speed, whereas this number 50 could completely describe the speed of this object because it wasn't changing, now that average isn't good enough because this thing is moving faster at certain times. It's moving slower at other times. So the thing we are interested in is instantaneous. This is kind of the guy. It's like having a speedometer in the car where we can know at this moment I'm moving this fast. I was going 30 miles per hour, then I speeded up to 50 miles per hour, then I went up to 70 miles per hour. Maybe I went back down to 40 miles per hour. Like I can see it instantly on the speedometer how fast we're going. That's what we want. We want the speedometer kind of perspective. We don't want to say, oh, it traveled this distance in this time. Well, on average, it was traveling this fast. No, At every instant along the way, how fast was it traveling, right? That's what we want to know. That is the gist of the rate problem. Like, can we measure in real time how quickly something is moving, how quickly something is changing, right? Now, we saw earlier that we could think of a slope as speed, right? Technically velocity. So now the question is, like, how do you find the slope of a curve? Because that would be the idea, right? So let's say here, right? Like I can say at this instant, what is the slope, right? It might not even make sense to call it slope, right? Because slope is a word that we use for straight lines, right? But the idea is the same. If there was a way to generalize the notion of slope, that's what I would be interested in. Why? Because in the simpler case, that kind of worked out to be equivalent to speed. I'm going to assume that it can be equivalent to speed here. And so the question is, well, how would you find the slope of a curve? And the answer, surprisingly, is to think like a flat earther, right? So it's a little bit of a joke there, but I'm kind of serious. The world, the earth is round, but if you are looking at it, a lot of times you can look as far as I can see and it looks really flat. And it looks flat because of the scale you're at, because you're so small compared to the earth, even when it's curved, it can still look flat. And so that's the kind of idea we want to use. The idea is, if I care about that point and I can zoom in, the more I zoom in, the flatter it starts to look. It was very curvy over here, but then I zoom into a larger scale and it starts to like flatten out, right? So that's the idea, right? So I'm going to kind of pretend the curve is flat. And I do that by changing the scale. I'm looking at it on a different scale. I'm just saying, well, if I were to zoom in, it would start to look flat, right? So you'll notice here, by zooming in, the curve appears, it's not actually flat. It appears to flatten out, right? So now you are saying, okay, it's starting to look flat now. And then you're trying to say, well, how would I describe this flatness? And the idea is it starts to get close to some straight line, right? There's some line that you can realize that if I keep zooming in, the curve will keep getting closer and closer to this line. So there's a flat line that I can use to approximate this curve at this point. The more I zoom in, the closer these two get together, right? So the more we zoom in, the closer the curve fits to this, or let me say, some line. We don't really know what the line is yet. We call this a tangent line. Tangent means to touch. It's the idea is that it touches it in one spot locally, but that's technically not true. A tangent line doesn't always do that, but that's where the name comes from. Wasn't chosen very wisely. Okay, so that's the idea. We know that the slope can measure speed, but if it's not a straight line, that's kind of weird. So the idea is zoom in so that it appears to be a straight line. If I were to zoom in and it starts to flatten out, what line would it look like, right? So the idea is if I zoom in, it would start to look like a line, and I want to know about that line. And so what we would do is we would define the slope of the curve to be the slope of that line, right? So we're going to say, well, the more I zoom in, the more it looks like this line. This line can be used to approximate the curve, right? And so that's what we're going to do. So now the question is, how do we find the slope of this line? Okay, now it sounds silly, but I want you to notice that we actually only have 1 point here, right? So if you don't know the slope of a line and you only have 1 point, how can you find the equation of the line? How can you find the slope from 1 point? Well, you can't, right? You need 2 points to find the slope. You need a y, x1, y1, and an x2, y2. Having one point is not helpful. So that's another problem, right? So how do you find the slope of a line? And the idea is you can use a secant line to help. So how is that going to look? So the idea is here is our curve. There's a point we care about right here, and there's a line we care about. That's the tangent line. And the idea is that tangent line would look closer and closer to that curve the more we zoom in. But I don't really know anything about that line. And I can't really know anything about that line because I only have 1 point. Let's call that point x and f of x. So that's all I know, this point. And that's not good enough. But here, if we can apply some space, man, space. So here, what we're going to do is we're going to put in a secant line. The same point. Right now, you're going to see the benefit of doing this pretty soon. And there's a punchline coming pretty soon. But the idea is, I can't really do much with the tangent line here. There's no way I can know what's going on. So what I can do is I can create another line. I can put in a secant line that passes through that point. So here I throw in my secant line. Now, what is the benefit of that? Well, now I get a second point. Now, of course, that second point is not on our tangent line, but we'll deal with that pretty soon. But here's where we get a second point. So let's say this point is h units away. So the second point we get is x plus h, which means that this would output x plus h. Okay. So now we have that, and we're like, all right, what do we do now? Because yeah, I can get 2 points with the secant line, but that's not the line I care about. I care about the tangent line. How can I get to the tangent line? Like, I know I can find the equation of the secant line if you give me these 2 points. That's no problem. Like, I can do that. We can have done that all the time, but the tangent line is still an issue here. So here's the idea. Move the second point close to the first. What would that accomplish? So what we can do here is we start moving that point up. How can we do that? Well, make the distance smaller so I can get, say, another point, and I would have that secant line. And I can make the distance even smaller. I would get another point, and I can get that secant line. And I can make this point get closer and closer, and I would get that secant line. And so you'll notice that there comes a point where, there comes a point, too many points, where this point is like right up on this other point, the point of interest. And it's in such a way that at that point, the secant line and the tangent line would look exactly the same. What you'll notice is that the secant lines start becoming the tangent line. And what we need to do is close the gap. Specifically this gap, the distance h. Essentially what I want to do is get one point to go right beside the other one so that when I draw a line through 2 points, which I need to do to be able to get the equation of a line, it's kind of like drawing it through 1 point because they're so super close together. They're not the same. I don't want the points to be the same because then I'd have 1 point. What I want to do is for 1 point to get super, super close to another point without actually being that point. So I don't really care about getting to that point. I just want to get super, super duper close to that point. And so now we're like, well, how are we supposed to do that? How do we get super duper close to something? Close, 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 like closer than anyone can complain about. Like anyone would agree that, man, that's closer than I thought it would get. Like every single person would say that. It has to be super close. How do I get that? What would that even be? And of course, some of you are probably thinking it right now. Well, that sounds like you're taking a limit, right? That's literally what the limit is. So we came here, we were studying the rate problem, right? And we did this, and then we got to this point, and we realized that I can kind of see a way to solve this problem, but I don't really have any mathematical machinery to actually do this legally. Like there's no math thing that I can just say, just turn the secant line into a tangent line. Like what does that mean mathematically? Well, that's what it means to take a limit. And that's why we went and we invented limits. We learned what it means to get close to something without actually being there. It was for the purpose of being able to solve this problem. But in order to do that, we have to build out a whole mathematical theory. What does it mean to take the limit of a function in general? And we did that, and I told you all about that, and we spent a lot of time on that. But the idea behind that was to do this. The only thing I wanted to do the whole time was to get the second point close to the first point so that the secant line would get close to the tangent line. So in other words, essentially we want h to get close to 0. Now, I never want h to actually be 0. I just want it to get close to 0. And that's where we realize, oh, we can use limits, right? Because that's what a limit is about. And the idea is a tangent line can be thought of as the limiting function of secant lines. So just like how one number can get closer and closer to another one, there's the idea of a line getting closer and closer to another one, and we'd call this line the limit of this other line. So it turns out like a tangent line is a limit of secant lines, right? Which we can get by this. By moving the points closer together, our secant line starts to get super close to the tangent line, to the point where no one can really tell the difference. The 2 points are so close together, they're not actually 1 point, but they may as well be 1 point. It's so super close that we can't actually see a distance between the two. The distance is literally going to 0. And so that kind of tells you the other big idea. This means that the slope of the tangent line is going to be the same as the slope of the secant line, but with one minor difference. We are going to take limits as h approaches 0 of that guy. This is going to be the slope of the tangent line here. I don't know, I'm getting too excited. Why did I put an exclamation point? So it turns out that's what it is. But what is the slope of the secant line? Well, we derived that earlier, right? It's literally the difference quotient. So this guy was the difference quotient. And so now we need to take a limit of the difference quotient. And that is, you might not realize it. It probably doesn't look like anything special, but this is actually the solution to the rate problem right here, staring us in the face. So limit above is super important, right? So we're going to give it a name, and I know my thing isn't. So one thing you want to know about one thing you want to know about math people and naming things, they're really just not very creative when it comes to naming stuff. So they would like name something just by what's going on at the moment. So they'd be like we saw earlier, right? The intermediate value theorem. Oh, there's this theorem that it tells us that we can attain all intermediate y values. What do you want to call it? Intermediate value theorem? They'll just call it by the name of the thing. And they're like, oh, this theorem is fundamental to the study of calculus. What do you want to call it? Fundamental theorem of calculus? Like they always name it something very obvious. But this limit, for whatever reason, I don't know what was the reason behind it. They decided to name it something totally different. They call it the derivative for whatever reason. It's like, yeah, just to be cool. I don't really know why it's called a derivative. I should probably look that up. But they just decided to like, let's throw the rules out. Let's not call it something like slope or like curvy slope or something that seemed super obvious. It's just like, it's called the derivative. And that's what it's called. It's called the derivative, right? So the derivative is a limit. And it's a limit that helps us to find the slope of a tangent line. And finding the slope of a tangent line helps us to find speed. It helps us to find rate of change. It helps us to talk about how much the output is changing in relation to the input, not just on average, but at every instant in theory, assuming this limit can be computed. So that leads to the definition of what we call the derivative. So given a function, the derivative of that function is this limit. We denote it by f prime. That's what that little notch there is called. It's called a prime, and it's that limit. And I did want to mention here, if f prime of x exists, then, because I'm going to use this later on, then f of x is called differentiable. Okay, so you have something called a differentiable function. What does that mean? It means I can compute this limit. Or I could say this function is differentiable in this region. What it means is I can always compute this limit in that region. I can find the derivative of this function. The derivative of this function exists because the derivative is really just a limit. It's the limit of the difference quotient as you make the distance between the points go to 0, right? And that just turns a secant line into a tangent line, essentially. Some more notation, there's the prime notation. That's what this is called. So this little thing here, this guy here, is called a prime. So when Isaac Newton was inventing his version of calculus, this is the notation he used for the derivative. I'm going to use it a lot of time because it's the easiest one to write. I just write the F and the little notch beside it. However, it turns out there was another mathematician, Gottfried Wilhelm Leibniz, who was a German mathematician, and he also, around the same time, invented calculus. He used a different notation. He used this guy, dy dx. That's how this is read. And that's because it's like you're taking the change in y over change in x, and you're making the distance in x go to 0, you get dy dx. So he went from the Greek letter delta to the English letter delta, and that's how he decided to do that. So this is the slope of the secant line. This is slope of tangent line. Right. So this is called Leibniz notation. It's actually a much more functional and useful notation, but in Calc 1, I'll mostly use this. When you're doing higher level math, chances are you want to use this guy because there are going to be multiple independent variables and all sorts of things can happen. Okay, so those are the notations for derivatives. So I could actually write this f prime, or I could write this as dy dx if we state that y is f of x. Right? If I said p equals f of x, this would be dp dx or whatever. So yeah. Now the interpretations of this number, well, we've already kind of spoken about it. How do you interpret what the derivative is? It's the slope of the function. It's what we define to be the slope of the function. More specifically, it's the slope of the tangent line to the function at that point, which it's another way of saying derivative, really. It's kind of a synonym for derivative. Derivative is kind of a more general term than slope. If you take the derivative concept and apply it to a straight line, you get what's called a slope. But the derivative is a much higher level concept. It's kind of like you can find the slope of almost anything. Technically, that it's incorrect to say that. You can find the slope of a lot of things that aren't straight lines. But when you talk about straight lines, you call it slope. If you're talking about anything else, call it derivative. And so the derivative is like the slope. It's also a measure of how fast f is changing with respect to x, or how fast the outputs are changing with respect to the inputs. And it's talking about the instantaneous rate of change of f of x at x. So yeah, those are all the interpretations. That might be useful for word problems down the road. So you need to know when you're computing this limit and you're computing a derivative, what are you doing? You're actually figuring out this stuff here. So let's actually do a quick example here. So here's a function, f of x equals x squared. I want us to use the limit definition of the derivative to find its derivative. And then in part B, use your answer to part A to find the equation of the tangent line to f at this point. And again, spoiler warning, I will ask you a problem like this. Okay, so pay attention to that. So we did all that mumbo jumbo just to get to this point where we could compute this limit that is called a derivative, and it gives us the slope of the tangent line. So let's actually do that here. So here, this is why literally like the first class, I had us do some difference quotient computation because you're going to need to be able to do it. This is why in pre-calc they annoyed you with doing it so much, because you're going to need to be able to do it. Need to be able to figure it out. So here f of x is x squared. And so f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Know this definition. As in the entire equation. There's a bad habit that students have sometimes where when you tell them to know a formula, they only memorize one side of the formula. Like they never memorize the whole equation. They don't know what the left side is. And you can get into a lot of trouble like that. So memorize the entire equation. If I ask you to define the derivative, I do expect you to write the left side of this equation. You can get in trouble otherwise. But that's the derivative. We just did that definition. So now we know how to do the difference quotient because that was pre-calc. We're literally going to go here. Everywhere we see x, we plug in x plus h. Everywhere we see f of x, plug in x squared over h. Now we want to take the limit as h approaches 0, but we can't because it's a limit. Try to plug in. If you can't plug in, you have to try to simplify to plug in. So we need to simplify the difference quotient, which again is something we know how to do. This is x squared plus 2xh plus h squared minus x squared all over h. X squared kills the x squared. And h is a common term in what's left over. Factor out that h, I would get 2x plus h over h. Now I can cancel the h's. And so now I would end up with the limit as h approaches 0 of 2x plus h. And hey, I can plug in h equals 0 now. So 2x is the answer. Now here's a way that we can state this. Because I will be using it in the future. We can say d dx of x squared is equal to 2x. And this is basically saying the derivative with respect to x, that's what this blue part is about, is equal to is 2x. Right? And that's because the Leibniz notation, as I mentioned, it's very versatile. You can actually factor this little y off to the side. And so you can write it as d dx of y. But in this case, our y was x squared. So I could actually write it like this. So this is a way to actually state like a thing, a rule that we have now. From now on, you can just know the derivative of x squared is 2x. That's actually something you should just know. We'll actually figure out a way to figure that out, but you should really just know that. But yeah, that's the answer, 2x. Now, part B. I wrote that B very large in relation to the A. Part B says, use your answer in A to find the equation of the tangent line. So we know what the derivative is. F prime of x equals 2x. This gives the slope of the tangent line. At x. Which means if I want to find it where x equals 3, so this means f prime of 3 is 2 times 3 equals 6. This is the slope of the tangent line at x equals 3. Now, to find the equation of a line, we don't just need the slope, we need a coordinate. So to find a point on the line, we know that x equals 3. This means that your y is equal to 3 squared, which is 9. So we have m is equal to 6, and x1, y1 is equal to 3, 9. This means that our tangent line is the following. Y minus y1 equals m x minus x1. So it's y minus 9 equals 6 x minus 3. And that's the equation of the line. I guess, or if I don't say you have to do this, you don't have to do it. You can rewrite it in y equals mx plus b form. So that'll be 6x, 3 6 is 18 plus 6x minus 9. Yeah. So that's the equation of the tangent line. And that's how I can find the derivative by definition. And so what this leads to is the following. Here I have the function x squared. Should do this side first. So here's y equals x squared. Now, someone told me, okay, I care about the point x equals 3, which is right here. This is at the point 3, 9. I want to find the equation of the tangent line at that point. So there is a straight line that is here, that passes through this point. I want to know what is the equation of that line. It turns out that line is y equals 6x minus 9. So it has y-intercept minus 9 and slope positive 6. And if I were to zoom in to this point, my y equals x squared curve would start to look very close to the line y equals 6x minus 9, because that's what the tangent line was meant to measure. So this is the tangent line. Right? So I can find the tangent line, and I can find the slope of the tangent line using the derivative. And out of this, I got a nice formula. So that's something we can remember now. We also got a formula out of this example. The derivative of x squared is 2x. Remember when you remember. Okay. Now, in some sense, there's nothing special about x squared in this regard in the way that its derivative was found. In fact, you can find the derivatives of a bunch of other things. And because we know the how to compute difference quotients, you can do a couple of these very quickly. And I would leave you guys to do the rest. So for example, what if we had a constant function? F of x equals a constant. What would the derivative be? Well, it kind of makes sense. this is just a constant function, f of x equals c, that's just a horizontal line. We would expect the slope equals 0. But is it? Let's see. What we would do here is f prime of x would be the limit as h approaches 0. Want to remember a definition? You just write it down every time. Minus f of x all over h. Now the thing is, f of x, c has no x's in it, so f of x plus h is just c. F of x is c over h. So here you just get the limit as h approaches 0 of 0 over h. Well, that's just 0, which makes sense. So this means that the derivative of a constant is 0. Remember, Winnie, remember. The derivative of any constant is 0, right? So it doesn't matter what the constant is. I can say, what is the derivative of 5? Well, the answer is 0. What is the derivative of e? Well, the answer is 0. What is the derivative of 17.9? Well, the answer is 0. What is the derivative of the square root of radical 2 plus 7 over sine of 30 degrees minus 14? The answer is 0. It does not matter what the constant is. For any constant c, the derivative is going to be 0. So that's another thing we got out of this. What about a constant times x? Now again, this is just a line. Undo. Cx is a line through the origin. So y equals cx. Here, c is like the m in y equals mx plus b, right? So we expect the slope to be c, right? Based on what we know about slopes, right? The derivative better give us the same answer. So that c is the answer c. Here, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So this would give you c of x plus h minus c of x over h. I think the camera froze for a while, then finally caught up. Okay, this here is cx plus ch minus cx all over h. This guy kills that guy. This is the limit as h approaches 0 of ch over h. This cancels with that. That's just the limit as h approaches 0 of c. And well, that's just c. So the derivative of cx equals c. Derivative of a constant times the variable, your independent variable, is always just the constant. In particular, when c equals 1, we get that the derivative of x is 1. Remember that. I'm going to do one more and leave these guys for you to do. does it do that? Can do that whole try these for next time. Find f prime using limits. But let's look at the radical x, just to wrap up the night with something not as trivial. Because radical x is the first one where I think the answer is not obvious, right? Like, if you have a tangent line here versus a tangent line here versus a tangent line, like, who would know what the slope is? It's hard to actually know what the answer, oh, it's obviously this, or the answer is obviously 0. Like, it's not obvious at all. Like, how do you find the slope of radical x? Well, now we know. We use that definition called the limit definition of the derivative. So it's radical x, so it's radical here of x plus h minus radical x all over h. I believe we did a problem similar to this. So I'm just going to spoil it for you. You multiply by the conjugate. So I'm going to multiply this by the conjugate over itself. This becomes that. Rookie mistake students always do, this is expand the denominator, never expand the denominator. You always want your denominator factored, because that way you can see if stuff will cancel. If you ever expand a denominator, it should only be temporary for the purpose of refactoring it, but usually it's very rare that that'll even happen. So never expand the denominator. In the numerator, though, it's now the difference of squares. I'm going to get x plus h minus x, and these guys are going to die. So here I have h over h times radical of x plus h. H's cancel. So now I have the limit as h approaches 0 of 1 over radical x plus h plus radical x. At this point, I can plug in h equals 0 without issue, as long as my x itself is not 0. Said x and started writing x. No, here I'm plugging in. So this is just going to be 1 over radical x plus radical x. Or in other words, 1 over 2 radical x. So this tells you that the slope of the square root of x is 1 over 2 square root of x. And that's something we know now. We know that by heart. Okay, so that's all we're going to do today. But hopefully now you see where the solution to the rate problem comes from, why it was the derivative, what the derivative is, what it was meant to measure, and why measuring that thing was thought of as like a rate of change or speed or how fast something is moving. It's because you extrapolated from a similar case to a more comprehensive case. But we'll stop there. Try these for next time. Use the definition to find the derivative of 1 over x and sine x. And yeah, we'll stop there. I don't think I have anything else. No. Properties of derivatives, yeah. But I wasn't planning on getting there here. That's why I just wrote the heading. I just wanted to remind myself that I need to tell you about that. Because sometimes I just use properties, but I don't actually remember to actually say them. So let me remind myself there. All right, we'll stop there. Sorry to late. So let's get out of here. You guys have access to the notes. Hopefully that's cool. Someone sent me something about homework in the chat. Just be sure to email me and I'll check on that. And yeah, that's it. Have a good night. Thank you for your attention. I'll see you guys in the next one. Ciao.